We're breaking down LeetCode 684 redundant connections today. We're going to cover this in Java. And while most people identified are able to build a brute force solution using standard traversals like DFS or BFS, people find it challenging to optimize the solution. That is because most people fixate themselves on standard graph traversals like BFS or DFS, but this problem can be solved in a much more optimized and cleaner manner using union find. And before we get into the solutions, we'll focus specifically on how do we identify that this or similar problems can be solved easily and idly using solutions like union find as opposed to standard graph traversals. So let's talk about that first. So if a graph is static and pre-built, a standard DFS or BFS would work just fine, and you will be able to identify cycles in an ideal way. However, that is based on the understanding that the graph is static and pre-built. If you look at the input here, you'll see that you're given an array of edges, which means which denotes that you have an incoming sequential stream of connections. Now, if you run a DFS every time you get a new edge, the overall time complexity degrades heavily, and that is your identifier of when to use union find. That is, if you're given a problem that requires you to evaluate the connectivity or identify cycles in a graph for a sequential stream of inputs, you should default to union find. Now we'll move to the actual coding part of it, and we'll cover for one of the example on how the normal explanation on how to get to the solution, and then we'll cover how the disjoint set or the union find approach works in a similar manner so that we are able to map it against our understandings. So this is a standard example from LeetCode where for a list of edges 1, 2, 1, 3 and 2, 3, we get the output as 2, 3. So the standard explanation for this problem is that without any edges being defined, all these nodes or vertices are like disjoint. They have no connectivity, they have no edges between them. The moment we get 1 and 2, we identify that 1 and 2 are now connected. So 1 and 2 are connected, so part of the same set. 3 remains disjoint. We get 1 and 3, we know that 1 and 3 are now connected, and 1 is already connected to 2. That means 1, 2, 3 are now connected, and there's no disjoint set. Now when we get 2, 3, we know that now 1, 2, 3 are connected. So if we connect 2 and 3 again, that's a redundancy. So that's where we detect the cycle. That's the normal explanation how we get to 2, 3. Now in a union find way, how does that happen? So similar to above, we initialize a parent array which denotes what are the known root or the parent for the current vertex. So before any edge is defined, we still have all of them in a disjoint state, saying that each vertex is a parent of itself because it really has no edge, so it's just connected to itself. Now whenever we get an edge, we say that if 1 and 2 have come, that means 1 is now, let's say, a parent of 2. And similarly, when 1 and 3 comes, we say 1 is now a parent of 3 as well. So every single time a new edge comes, we figure out what are the parent of this both edges. So initially for 1 and 2, we say 1 is the parent of itself and 2 is the parent of itself, which means both are unique, do not have the same parent. We can merge them. When we merge them, we now update saying that 1 is now the parent of 2. So when we get 1 and 3, we say 1 is still its own parent, 3 is still its own parent, so 1 and 3 can also be merged, and 1 is now parent of both 2, 3. Now when you get 2 and 3, now 2 has a parent of 1, 3 has a parent of 1 as well, which means both of them have the same parent. So if you visualize it as a form of tree, you will see that 1 at the top and then 2 and 3 are both connected to 1, which means that they're already a tree structure. And now if you want to connect 2 and 3, and both of them have a common node, common parent, that means you're introducing a cycle. So that's how the union find works. That's how it detects a cycle in a graph. Now this is the main method, which basically has the same input as above, and this is the method that we have to code using the union find approach. Now if you note, we have written union find with path compression. There's also additional optimizations like rank. We'll get brief into it, but for most purposes, union find with path compression is close towards the ideal solution in most scenarios and is acceptable. So we'll focus on that mostly as part of this video. So yeah, so the base of union find is defining and storing parents against each node. So we'll define an array of parents. Now parents array has to be initialized, and the overall length of the array is equal to the overall number of vertices. So this edges length as per the constraint is equal to that overall length of the total number of vertices. We've added +1 here, and if you note, +1 is specifically because for this LeetCode problem the edges starts from 1 as opposed to 0, and we want to avoid any -1 logic everywhere for the sake of simplicity. But you can have edges of length as well, and then everywhere we can have a -1 to denote the actual representation. So I'm going to give +1 for now, and then we are going to initialize the parents array, and we are going to mark each we're going to initialize it. We're going to mark each node or vertex as a parent of itself. So parents of I would be equal to I. Now this means our parents are now initialized. We are in a state where we are saying that all of them are the parent of themselves. So moving next, what we do is we have a list of edges, so we'll start accepting one edge at a time, and we run the same logic that we discussed above. Figure out the parent for both vertices. If the parents are same, that's our faulty or the cyclic or the edge that creates a cycle. We return that early, and if there's no cycle, that edge is accepted, we'll update and mark one of the vertices as the parent of another. So let's write that down. So first thing first, we're going to do parent of x and y. At this time I'll use for vertex x and vertex y, denoting the two vertices for edge. So this would be a find method, the general name we use in union find. We'll code the find method in a bit. We'll just pass the x coordinate or the edge of 0 for it for now, and similarly we'll have parent of y, which would be on the edge of 1. Now at any point of time, if both these parent x are equal to parent y, that is our identifier saying that we have to return this edge, because if both parents are the same and you're adding an edge, you're creating a cycle. And in case there's no edge detected, then we simply say that parents of parent y, let's say, or parent x, let's say, is equal to parent of y. This is where we are saying that, or I'll probably write down a comment here as well. We're saying parents are same, this edge will create cycle, and this would become parents not same, disjoint set unifying, right? Now obviously this is where an additional concept of rank will come in, and I'll come to that in a bit. But yeah, this is our quotient gates against our quotient says that it will always be an edge, but still for the basic return case we say that no cycle was detected, so we return new int of 0. Now we have one more method to code, which would be the find method, which returns the parent for any given node. So let's say this is the node, and we have to return the parent corresponding to it. So the first thing first is the base condition. We define if parents of this node is double equal to node itself, which is basically us saying that if we have encountered a node that does not have any parent, it points to itself, we'll return that node, that's the top parent. And if that's not the case, then we will return the parent of the current node's parent, which is basically we want to identify the top parent at any point of time. Now this is not optimized. This is order of n square. Now we can optimize it, saying we want to assign parents of node should be equal to find parents of. This is path compression, which is basically we are updating the results for each node whenever we are computing the parent, so that for future computations we don't have to do as many iterations, and the overall worst case complexity comes down from order of n square to order of n order of n log n. So yeah, this is the return node. So this is it, and I will go to the rank in a bit. I'll save this. We can run it now. So you see, we get the same result that we were expected. We'll also test it out for some other results. So let's say this one. So this one has this such, and the expectation was this. So okay, so C is this, and yes, we have 1 2, then we have 2 comma 3, we have 3 comma 4, we have 1 comma 4, we have 1 comma 5. Yes, so we save it, this, and we get 1 comma 4 as expected. So this is working fine. So this is an order of n log n time complexity and order of n space complexity solution. We can reduce the complexity even further by the concept of rank, which is where instead of randomly assigning parent x to parent y or parent y to parent x, or we find out based on the rank which is the more optimal parent to assign to the other node, which would help us reduce the overall number of iterations, bringing down the complexity to order of n, alpha n, which is for all practical reasons close to order of n. Yeah, so that was the solution. We'll probably cover the rank in some time future as well. For most of the coding problems or coding competitions, or even in interviews, union with path compression is a much more acceptable solution. Rank is obviously even better optimization on top of it, but for most practical reasons, path compression is a very much acceptable solution at all point of time. So that's it for this video. We'll probably cover more in the future. We'll keep our focus more into understanding how do we identify patterns, because I think that's the most critical part of it. And once we understand how do we identify pattern, then how do you implement it, and how do you write the code in a way which is simple, easy to understand, and easy to maintain. So that's it for this video. Thank you.